Hello, am I audible? Hello, am I
Yes, sir.
audible?
Yes, sir.
Okay, good morning and welcome to lecture on advanced power electronics. Last time we discussed control of three-phase bridge inverter and very basic things we have discussed and three methods of controlling we have discussed. The first method is 180 degrees mode of conduction. After that, 120 degrees mode of conduction. This 180 and 120 degrees mode of conduction is not used in the practice. And in the practice, we are used various PWM techniques. We have listed the various PWM techniques. These PWM techniques, these PWM techniques are a sinusoidal PWM, then selective harmonic elimination, SHE space vector PWM, hysteresis uh, band current control PWM, sinusoidal PWM with instantaneous current control. And out of that, what we are discuss is only we are interested in the sinusoidal PWM. Other PWM techniques we'll discuss in due course of the time. And now we have discussed this sinusoidal PWM, how we obtain the switching signal for these six devices. So our devices, we are having one leg, we are having devices S1 and S4. And for that, we are comparing two signals, a carrier wave, a triangular wave signal, which is of constant frequency and a constant magnitude. Carrier wave is compared with V1. Okay. And this we are generating the two switching signals, and these two switching signals we are given to S1 and S4. For switching signals for S3 and S6, we can obtain by comparing the carrier wave with respect to the second modulating wave V2, which is phase shifted V1 by an angle of 120 degrees. On the similar, we generate the switching signal for S5 and S2 by comparing the modulating wave V3 with the carrier wave. And now last time we discussed how we get we make one fictitious point, n point here at the negative of the DC rail. And with respect to that, we obtain the AN. When S1 is on, when switch S1 is on, our AN will be a plus VDC. And when S4 is on, our VAN will be 0. So we are knowing already this is switching signal how we generate, and based on that we get the VAN. So where our particularly if you see it here, our modulating wave is higher than carrier, so our switch S1 is on, and as S1 is on, we'll get the plus VDC. Now, if you go for a second, in this case, particularly our modulating wave is less compared to a triangular wave at this instant, and S4 is on. And when S4 is on, output voltage will be 0. So this is done for first leg. Similarly, switching signal for leg 2, our BAN will be a positive VDC when S3 is on, and VBN will be a 0 when S6 is on. And once you know the VAN and VBN, it is a common point. So VAB, a very straight way, will be VAN minus VBN. So we can write it here. So our VAB that is the output line voltage VAB will be equal to V AN. It is not the N is a fictitious point, not the our VAN is a phase voltage. VAN minus VBN. Here AN and BN are not the phase voltage. It is just the point N we are getting with this, and we obtain the line voltage waveform, and we have seen that dotted it is shown. What dotted is shown is the our fundamental component of output voltage. It is having some high frequency harmonics, but we are having definitely the output voltage. And how we control the output voltage? Output voltage we control by controlling the magnitude of modulating wave, and peak amplitude of modulating wave to the peak amplitude of carrier wave, that we can call as a modulation index. And this m is varying from 0 to 1, then we can call as a linear range, and above 1 we can call as a over modulation. So we control the output voltage by controlling the modulation index, whereas frequency is controlled by controlling the frequency of modulating wave, and phase sequence is controlled by controlling the phase sequence of these V1, V2, V3 signals. So this is the line voltage waveform, just whatever we have drawn it here, the same we have shown it here, and the phase voltage is having 1/3 VDC and the 2/3 VDC. This is a lower wave shape is the phase voltage, and upper is the line voltage. And we have seen that this is our particularly graph indicating how we control our x-axis is a modulation index, and we have defined m will be given by peak amplitude of modulating wave, Vm you can call it, peak amplitude of modulating wave divided by peak amplitude of a triangular wave, we can call as a Vt. So ratio of Vm by Vt you can call as a m. We have shown it here, m equal to 1. Our m may go up to 4 or 5 here, and up to we have seen that when m equal to 1 we'll get the 78% of the output voltage of the 180 degrees mode of conduction. So here if you shoot 1 here, this comparison with this, and here m comes out to be around 3.24. When m is 3.24, our PWM is switched to a PWM will be switched to a 180 degrees mode of conduction. When our modulating wave is around 3.4 times than that of carrier wave, then our inverter will become as a square wave inverter or 180 degrees mode of inverter or a 6-step inverter. And comparing with 6-step inverter, our output voltage of sinusoidal PWM is a 78%, 78.55%. And whenever m is very large, when m is greater than 3.24, more than this, then we are getting into a square wave inverter operation. Another name for square wave inverter operation is 180 degrees mode of conduction or the 6-step inverter. So with this background, okay, we discuss the review the inverters. Also, we review the converters, and we have seen that converters has two drawbacks. One is they will take a lagging reactive power from the supply. They operate at the lagging power factor, and there we have seen that THD they will take a non-sinusoidal current, and these are the two drawbacks. And we want to eliminate these two drawbacks of the thyristorized rectifiers. And this problem particularly we can call as our conventional inverters are conventional thyristor converters are injecting current harmonics, and we want to mitigate the harmonics, and for that we are in various filters are available. One is active filter that we'll discuss in this course. A passive filter you are discussing another. Here we are having another is a power factor correction converters. A converter which will operate at the unity power factor, and the hybrid filters. Okay, hybrid filter is a combination of active filter plus passive filter. So this filter is one option, whereas another is instead of going for our thyristorized converter, we can change the converter itself, and that we can call as a PWM converter. So that will be our starting of our particular this subject. We are starting with our PWM converters, or you can call as a PWM rectifiers. So this will be coming under power factor correction converters. These are PWM converters, and basics required for that PWM converters are the whatever inverter basics are required, and that already we have discussed. What are the features of these PWM converters? We are going in detail, but at this present, we can say the features of these PWM converters. It is a basically AC to DC converters. So we convert the AC power into the DC power. So it is doing the job of rectifier. AC power is converted into a DC power. That is the job of PWM rectifiers. So AC power is converted into a DC power. That is the job of this PWM converters. But what they are, they can work at unity power factor. They will not take the reactive power from the supply. That is very, very important. So whatever PWM converters or rectifiers we are discussing, they will convert the AC power into the DC power. They are doing the job of thyristorize converters, but very, very peculiar feature of these PWM converters is they work at any power factor. Means they can work at unity power factor, lagging power factor, as well as leading power factor. So which operation we can prefer? Okay, we can prefer for the unity operation, unity power factor operation. Or if you want to compensate the lagging reactive power of other loads, then it is also possible that you can work with the leading. But normally we can say that we cannot take any reactive power from the supply or give the reactive power to the supply or grid. In that case, our operation at unity power factor is. And very, very important, it takes a sinusoidal current from the source. It takes a sinusoidal current from the source. So whatever the drawbacks of these thyristorize converters, they are completely eliminated with the help of PWM converters or the PWM rectifiers. And these PWM rectifiers we can call as ideal rectifiers from power system point of view, because they operate at unity power factor and they will take a sinusoidal current from the power supply. So this PWM rectifier will work like a resistive load on the power system. They will work like a linear or non-linear load. PWM rectifiers will work like a linear or non-linear load on the power system. Can you tell anybody unmute and tell me?
Linear load.
This PWM converters will work as a linear load or the non-linear load on the power system.
Linear load.
So they will work as a linear load on the power system, and reason is they take a sinusoidal current from the supply and they work at unity power factor. And now we are going to classify the PWM rectifiers, which will we are having AC to AC power is converted into the DC power, and we are having based on input whether our supply is a single phase or three phase. When we are having a single phase AC supply, then we can call as a single phase PWM rectifier when the supply is AC single phase, and when supply is a three phase, then we can call as a three phase PWM rectifiers. And we have seen that when we can call as a voltage source and current source, when our output DC is a voltage source, then we can call as a voltage source PWM rectifier. When output DC current is in the form of current source, then we can call as a current source. So depending upon what type of DC source we are obtaining from the PWM rectifier, based on that, we are having a voltage source PWM rectifier and current source PWM rectifier. So this is the classification of PWM rectifiers. One classification is based on input supply, whether it is a single phase or a three phase. When supply is single phase AC, then it is called a single phase PWM rectifier. When supply is three phase, it is three phase PWM rectifier. And what type of DC output voltage we can obtain based on that. If our DC output voltage is a voltage source, then it is called as a voltage source PWM rectifier. And when the output power, DC power, is in the form of current source, DC current source, then it is called as a current source PWM rectifier. Now let us start with single phase and voltage source. So we take the combination of this, a single phase voltage source. So we'll take a single phase and the voltage source, and that will be our a single phase voltage source PWM rectifier. So here we have shown the circuit diagram of this single phase voltage source PWM rectifier, and which devices we can use for this. Here you see this is our single phase supply we are giving to this, and the load where we obtain the DC supply. So here at the output, particularly load, we are having upper terminal is a positive, lower is a negative. So this is our DC output, and here we are use the devices. Which switching devices you see it here in the diagram. Particularly in the diagram, we have shown the IGBT. So our devices used are here IGBT. 4 numbers of IGBTs are used here. They are given just not our particularly bridge inverter configuration, but we are given numbers are somewhat different. We have given it. So first leg device numbers are we are having a 1 and 2, and second leg device numbers are 3 and 4. Okay, just we are taken from one paper, and we stick to this convention, particularly for a single phase voltage source PWM. And devices used are insulated gate, bipolar transistors. You can use it here. What other option is available? What other option is available to IGBT here? Instead of IGBT, which other device we can use it here? Anybody? Anyone? Hello? Am I audible? Hello?
Yes, audible.
Yes. Instead of IGBT, which other device we can use it here? Which other device we can use?
Power MOSFET.
Yes, loudly.
Power MOSFET.
Okay, correct. So we can use the power MOSFET or the IGBT. Here we have shown in the diagram is IGBT. And here we have shown the 2 passive components. Okay, we have shown the 2 passive components in the circuit. And in that, one is inductance and other is a capacitor. So here we require what essential circuit components we have shown it here. We require 4 full control switches, maybe IGBT or MOSFET. We require passive components, 2 passive components. At the input side, we require an inductor, and at the output side, we require the capacitor. Now here, we are already discussed here. This particular is a PWM rectifier, and as we are just discussed this feature, it can work at unity or leading power factor. We are going to discuss this, how it works at unity or the leading power factor or the lagging power factor. So that is a feature. I take what takes as the sinusoidal current. That is also we have just listed earlier. And now here, basically here one important thing, it is requirement is that what are the requirements for this particular single phase voltage source PWM? First requirement is we require these 2 passive components. We require these 2 passive components. Without this, it is not possible. This is the first requirement. And second is, if you see the output voltage and the source voltage, here Vs is the AC voltage and VO is the DC voltage. So particularly for satisfactory operation of this particular PWM rectifier, our output voltage, DC output voltage, should be greater than peak value of supply voltage. Maybe a 1.5 times we can take it peak value of the supply, but definitely it should be required to a peak value of a supply voltage. Okay, so here let us assume that we are having a supply is a 230 volt single phase AC supply. Let us assume that we are having a 230 volt a single phase supply here. Then how much should the minimum DC voltage above which we can control this? We can, so there is a limitation on the output voltage. So if you are having a 230 volt, uh, peak value of that is 325. So at least this voltage should be a 350 or 400. So here we say it here. So if input is our 230, so ideally maybe we can go for 400 volts. Minimum voltage is 400. Okay, minimum voltage is 400. And what should be the maximum voltage we can obtain in case of boost converter? How much times of boosting is possible? How much time of boosting is possible in case of DC to DC boost converter? How much times we can boost? Let us assume that 7 times. So here definitely we can go our maximum output voltage, we can go up to 2000 or 2500 volts. So let us assume it here we are going for a 2000 volt. So what will be our output voltage control range? We control the output voltage, DC output voltage. What is the minimum voltage and maximum voltage? Our minimum voltage is how much? 400 volts. Why it is? Because under normal conditions, our diode should not forward bias. Our diodes should not forward. These diodes should not forward bias under normal operating conditions. And to get the reverse bias, definitely our DC voltage should be higher than the AC voltage. And so that here we cannot go the control of voltage below 400. So it is not possible to go below 400. If you just go, then we cannot get the benefits of this. Benefits of sinusoidal current and the unity power factor is not possible whenever we are going the voltage below 400. When our voltage is below 400. So ideal range is, so what we are having, so our range is 400 volts minimum. We can go up to 5 times or 6 times. So maximum voltage is 200. So whenever our input voltage is 230 volts single phase 50 hertz, what is our output voltage range? Our output voltage control range is a 400 volts to the 2000 volts. So we get a controlled output voltage. So what we say that output voltage is possible to control. So we can control the output voltage. We can adjust 400, 500, 1000, any value it requires. And for that, when you want to have a controlled DC voltage, another is it will work in the closed loop control. First thing is it will work in the closed loop control. Open loop control is not possible. So what is the drawback of this particular single phase voltage source PWM rectifier? It will not work in open loop. Our diode bridge, our thyristor converter, it will work in the open loop. Just give a particular alpha, it will give the output. But and here we have shown it here. In case of the single phase voltage source PWM rectifier, it will not work in the open loop. It will work only in the closed. And we have shown it here. Particularly, we are having here input is AC supply, and particularly our power can be a bidirectional. So this particular configuration, power can flow from AC side. Power can flow from AC side to DC side. If you see it here, and that is our rectifier operation. This is our rectifier operation. Power is flowing from AC, and it is also a power can flow from DC side to the here. If you are having a battery here, then this battery can be discharged into the grid, and that power can be flow inverter operation. So the power flow is bidirectional. Power can flow from AC side to the DC side, or power can flow from DC side to the AC side. And now we have discussed it for this single phase voltage source PWM rectifier has to operate properly, which will be takes a sinusoidal current from the supply and operates at unity power factor. Then what should be required? And that is what is our requirement. We have given it here. Essential requirement, we require the inductance. Okay, for boosting of the voltage, we can say it here, we require the inductance at the source side. Okay, we want the inductance at the source side, that is must. Also the capacitor at the output side, so we require capacitor also. Our output is a DC voltage source, a voltage source PWM, so we require a capacitor at this. And we have shown it here, open loop control is not possible, so it will work with a closed loop control. So it will be required to be a closed loop control. So we discuss what should be the input voltage range. It should be controlled in closed loop. We require inductance at the source side, and we require capacitor at the output side. With this, now our interest is how the source current is maintained sinusoidal. Now let us go for its operation. Now how this converter will take a sinusoidal current from the supply. Any question? Am I audible?
Yes, sir. You are audible.
Any question? Any doubt?
Sir, here what do we mean by like closed loop control? What is given in feedback, sir?
Okay, we are going to discuss this. So we are taking the feedback as the output voltage. Okay, we are having a set reference and we control the output voltage with the closed loop control. Okay, we are going to discuss this. So just now, after few slides, 1 or 2 slides, we are going to discuss the closed loop control. Now our interest is how the current taken from the source is the sinusoidal current. Let us, we have taken these 2 points P and N. I think they are visible. This one point is P, a positive DC link, you can call it a negative DC link. This P and N points. And now whatever our voltage here, inductance points, okay, switches. So let us consider the case. We have seen that our 2 switches, a T1 and T4 are on. Our 2 switches, let us assume that T1 and T4 are on. So what will happen? We are considering the positive half cycle of AC wave. So here Vs is our AC supply voltage, and we are considering the positive half cycle of the AC voltage. And in that case, we assume that our upper terminal is positive. And now this, let us T1 is on. So inductor through this switch, it will be connected to the capacitor positive. Okay, so inductor terminal is connected to a capacitor positive. Okay, so it will be a, I'm just showing it here. So P point, now P point will come at this particular instant. So if you see it here, I'll just show with a laser. So here this P point, those switch is on, it come at the inductor, or now inductor and a positive terminal of capacitor, then through the N, and then through N through a T4, it will be connected to the negative of the source. So here this is our equivalent circuit. If you see it here, equivalent circuit when T1 and T4 are on. When T1 and T4 are on. When T1 and T4 are on, we have seen it here. Now what will happen to the particularly the current? Our Vs and VO, which will be higher? Vs is higher or VO is higher? Which quantity will be higher? Our quantity higher will be VO, and we switch on VO, and this capacitor voltage is opposing the supply voltage, and the capacitor voltage is higher. We are assuming that power is going from AC side to the DC side, and under that condition, the capacitor will oppose. Because of the polarity, capacitor will oppose the increase of current. Capacitor will try to decrease the current under this condition. So what will be our, we can say it here, when T1 and T4 are on, particularly what is the supply current tendency? Supply current tendency will be to decrease the current. So current is decreasing. Okay, let us assume that our current is decreasing. So what will happen to the di by dt? Now current will be flowing this, but it is decreasing. So it will oppose this. Is it right? So inductor voltage, this will be coming as positive inductor voltage, and this will be a negative. And the supply voltage plus inductor voltage. In our this closed loop circuit, we can say that Vs plus L di by dt. Okay, inductor current is decreasing, and so that will become equal to the particularly capacitor voltage. So I think it will be clear when T1 and T4 are turned on in a positive half cycle of AC voltage, particularly we can say that our source current has a tendency to decrease, and supply voltage plus inductor voltage will be equal to a capacitor voltage. That is okay, our circuit equation. Now let us consider our other two switches are on. So let us go for other two switches. Let us assume that our another switches T3 and T4 we made it on. So T3 and a T4, sorry, T3 and T2 we can made it on. When these two are made on, now what will happen? Now you see the P point. This is our, okay, this is the inductor point is now connected to the opposite side of the capacitor. So this will be a negative and this will be a positive. So when you switch on T3 and T2, we have seen that when T3 and T2 are on, now you see the supply voltage, Vs, and the capacitor voltage. What they are having? Now the supply voltage and the capacitor voltage both are additive in nature, and because of that there will be a increase of current. So current will try to increase here. So current will have a tendency to increase, and as current has a tendency to increase, we can say the inductor will try to oppose this. So polarity developed will be like this, and this particularly we can say it here. So this will be when we switch on the T2 and T3, particularly these are the polarities of inductor, and current has a tendency to increase. So here current has a tendency to increase when T1 and T4 are made on. We have seen it here, current has a tendency to decrease. Whereas let us assume that third case, our T1 and T3 are on, upper two are on. So what will happen? Our inductor will be a shorted. Is it right? So whenever we are having this third configuration, T1 and T3 is one configuration. Here T1 and T3 are on. T1 and T3. The third case we have shown it here. When T1 and T3 are on, our inductor will be shorted, and depending upon whatever energy stored, the current will be maintained in that direction. So we have considered the how the inductor current can be shaped. So how we shape the inductor current? How we shape the inductor current? How inductor current is controlled? Is it clear? How inductor current is controlled? Inductor current is controlled by connecting a capacitor voltage across the series combination of a voltage source and the inductor. And this capacitor voltage may be additive with respect to supply voltage. When the capacitor voltage is additive, this case T1, T2 and T3 are on. When capacitor voltage is additive with the supply, our current can be made increased. And if the capacitor voltage is opposing to the supply voltage, the current can be reduced. So by switching the capacitor polarity, by properly switching the capacitor polarity with the devices T1, T2, T3, T4, we can say it is possible to decrease the current, it is possible to increase the current. Means inductor current we increase and decrease. It means that we can control the inductor current. We can control the inductor current. So whatever we discuss, we can write it here. What will be our inductor voltage? L di by dt. And this inductor voltage will be a difference of this inductor voltage is a difference of supply voltage and the capacitor voltage always. And so here we can write the expression VL, that is voltage across the inductor, will be L dis by dt, and that is supply voltage minus KVO. And K is nothing but when K will be 1, first case, minus means current will decrease. So here K will be 1 when T1 and T4 are on. K will be minus 1 when T3 and T4 are on. And K will be equal to 0 when T1, T3 or T2, T4 are on. So one for this case, two possible combinations, upper two may be on or the lower two may be on. So this will be our how we control the voltage across the inductor. We are controlling the voltage across the inductor. It means we are controlling the current through the inductor. And this inductor current, whatever this inductor current is nothing but the source current. Inductor current is nothing but the source current. So we control the source current. Now let us go for, we are required a closed loop control. What we discuss is, we are saying very earlier that we have to be a closed loop control. And for obtaining a closed loop control, what is essential? So here we have to control the output voltage in the closed loop. So we take a feedback from output DC voltage. So this is VO. We can take a feedback from the voltage across the capacitor. This feedback we can take, we set with a reference. So this is our output voltage reference. We can set it. And this is VO is the feedback. So this is our feedback voltage. So this is a feedback from where we can take a feedback. This feedback we can take from the capacitor voltage. Okay, so capacitor voltage, you can say it here. A feedback is we are taking from a capacitor voltage. Okay, and we are having a reference voltage. Our reference voltage, this error we generate, this is we can call as the E. E will be a difference between the VO reference minus actual VO, that we get the E. Okay, we get the error, and this error is given to a controller. I think you have studied various types of controller. Conventionally we are having, can you just name the controllers? One is P controller. Are you aware of that? P, then next we are having is
PI.
PI, and then third we are having is
PID or PD.
PID or P. Okay, PID. So in case of particularly our power electronics, normally we are going for a PI control. Okay, time constant system is less. So normally 99% cases we are using the a PI controller. PID may be okay, but normally we don't have a much dead time in the system, and because of that, normally we are going for a controller that will be a PI controller. So here, whatever error between the reference voltage and the feedback voltage, so whatever error we are getting, this is a reference voltage we can set. And now how much reference voltage we can set? We have just shown it here. What should be our output voltage range? We can set the reference maybe 400, maybe 1000, maybe 1500. So this will be our reference. We can set it, how much DC voltage we require at the output, that we set the reference. We take the feedback as the capacitor voltage. We generate the error, and this error is given to a PI controller. This error is given to a PI controller. So our VO reference is a positive voltage. VO is also positive voltage. Error is a positive voltage. Then what will be output voltage of the voltage controller? It is a AC or DC. Output voltage available from the voltage controller what type of output voltage we can obtain from the controller with respect to time. Let us assume that our x-axis is t. What type of voltage we can obtain?
DC.
A DC. Okay, maybe a slow varying depending upon the changes in the whatever the values of output voltage and reference. But this voltage is a maybe slow varying, but it maybe you can say it is a DC. So this is the output voltage of voltage controller. This is we can call as our this water with respect to time. So we get a DC voltage here. Okay, we get the DC voltage VDC here. Now this DC voltage, we have to multiply with unit magnitude sinusoid. This Vs is what is the wave shape of Vs? Vs is the we taken from the supply, but its magnitude we reduce it, and this will be in phase with supply, and its magnitude is unit magnitude. Means its peak amplitude is 1. Its peak amplitude will be equal to 1. Okay, this is our what we are having is a Vs. Vs is a unit magnitude sinusoid which is in phase with supply voltage. So now if you are getting this, then we get a current reference multiplication of PI controller output voltage, which will be a DC. Let us assume that this DC at particular instant magnitude is 50. Okay, so it is a 50 volts. Let us assume that magnitude is a 50 volt of this. Okay, let us assume that. Okay, magnitude is up in this range, and we multiply with the unit magnitude. Then here, what will be our current reference? Current reference will be sinusoidal, and what is peak amplitude? Current reference will be a sinusoidal, and what will be its peak amplitude? How we get a current reference? How we obtain the current reference? Current reference, if you see it here, current reference is multiplication of two things. Is it right? This is output, this particular we can call as current reference, and current reference is the multiplication of two things. What are these two things? One is a unit magnitude sinusoid. So this is a unit magnitude sinusoid multiplied by a constant voltage. So this peak will now become as how much? VDC. Output of the controller voltage, that will now become as the peak of this. Now peak of this will be a VDC. Okay, sorry, here not a VDC. You can you can get a VDC name or output of controller, whatever this output of controller, that will be a magnitude. So here we get the current reference. Is it clear? How we obtain the source current reference? How we obtain
Yes.
any doubt? Hello?
No, no doubt, sir.
Okay, so we get here a sinusoidal waveform, but its amplitude will depend upon the output of voltage controls. And now here we are current reference is there. Then we take a feedback current that will be from the inductor current. So we take a source current, and this particular feedback you can call this name as the, what is the name? A source current. Source current, IS. Okay, that will be our IS. From where we take from inductor, putting a series, we get the source current. And these two currents we compare and giving to another controller, and that controller is called as a current controller. Name, again, it can be a PI controller. The second, particularly this particular controller, current controller, can be a PI controller. We are getting the two. One is we get a I reference, we get a source current feedback, we generate the error, and from that we can get the output. So for current controller, we can use it a PI controller, but PI controller output is a DC. Again, that we want a switching signal. Instead of that, we are having another option for the current controller, and that option is nothing but a hysteresis control. We can use a direct, if you use a hysteresis control, we direct get the switching signal for the all the four devices. So here current controller, two options are available. What are these two options for current controller? One is PI controller, similar to what we used earlier, voltage controller. So one is a PI and other is hysteresis, but which will prefer at present? At present, we'll prefer the hysteresis control. We prefer the hysteresis control. And how the hysteresis control work? Okay, that we can discuss now. Any question? So current controller, two options are available. One is PI, other is hysteresis control. So let us consider that, okay, hysteresis control first, then how we can go for this. So now whatever we discussed, just we have summarized it here. Okay, proportional and integral control, PI control, normally we can use for our all power electronic systems, we can use proportional and integral controller. And you are knowing what is the PI, output of PI is proportional to error of the signal, error applied, and integral of the error, whatever we are applied to the controller. And very feature characteristics of this PI controller is a steady state error will be 0. Means reference and feedback will be always the same. And here output of the voltage controller we can term as a current reference. Output of voltage controller we can call as a current reference. And output of PI controller is the DC value. And now with this, now we can go for how the hysteresis control will work. And now here we are shown the I reference we can get. Is it right? So from this, our output of a particular this voltage controller is the I reference. If you see it here, we are getting the this is our I reference we are getting, and this I reference is sinusoidal. This I reference will be sinusoidal. So now here this comparison and all we can call as hysteresis controller. So we are knowing the I reference, so we can go for the I reference here. So this is our I reference is sinusoidal. I am just tracing the I reference of this. Okay, if you see it here, this is a in between that we are having a current reference. This current reference is what is this? We are having it is a sinusoidal. We have shown halfway. Okay, we have shown it the half here. So whatever I have made it with red, that will be a current reference. Okay, that will come from output of PI controller, voltage controller multiplied by the unit sinusoid. So you will get this will be a current reference. Now in case of hysteresis controller, we are having a window. So that lower and upper band is there. And that upper band, I will just show this will be upper band what we are having. This will be our upper band of, sorry, it is this is upper band, and then we are having a lower band. Let us go for this is the lower band. Okay, so what we are having is the upper band and the lower band, and that we can call as a hysteresis window. A reference lower band, that is hysteresis band, upper hysteresis band, and the lower hysteresis band. Okay, and the total will be twice the hysteresis band. And now our current, actual current will remain within that band. Now if you want to increase the current, which devices we want to switch on? Now let us assume it here. So now we can, how it will operate. Let us assume that I want to increase the current. Which two devices we can switch on? If you see it here, diagram of single phase voltage source PWM rectifier, we want to increase the source current. Which two devices we can switch on? Hello? For increase of current, which two devices we can switch on for positive half cycle of current?
T1 and T4.
T1 and T2 are in one leg. Okay. So if you just go back this slide, okay, just to recall. So here for increase of current, this is the case when T2 and T3 are on, we increase the current. Is it right? And when T1 and T4 are on, when T1 and T4 are on, current will decrease. Then T2 and T3 will be on, current will increase. So with this, now here I want to increase the current. When current will increase, our T2 and T3 will be on. It reaches to upper band. And when it reaches to upper band of current, what action I want? I want to decrease the current. How I decrease the current? I turn on the T1 and T4. When you turn on T1 and T4, our current will decrease. When the current T1 and T4 will remain on till current reach to a lower hysteresis band. At lower hysteresis band, at this point, what I am showing, we want to increase the current. So for increasing current, which devices we can switch on? T2 and T3. So we can switch on the T2 and T3. If you want to decrease the current, we switch on T1 and T4. If you want to decrease the current, I want to switch on T1 and T4. So depending upon the requirement of current, whether it is an increasing current, when current increasing is required, we can go for T3 and T2. If you want to decrease the current here, if you want to decrease the current, we switch on the T1 and T4. If you want to increase the current, we switch on a T2 and T3. And this is the switching signal we can obtain with the help of this logic particular. Is it clear? So how we control the current as within the band? We are getting the reference signal from the output of PI controller multiplied by the unit sinusoid magnitude. So here unit sinusoid, we get the I reference, and this I reference is nothing but the sinusoidal waveform. Half cycle we have shown. Similar, you can continue for another half cycle. And our actual current, that is the source current. Actual current, whatever here increasing, decreasing current, that current is remaining within that band, and that band can be adjusted to a small value, so that our source current will be a sinusoidal. Source current will be varying within a small band. If band is less, what will happen to a switching frequency? If band is less, what will happen to a switching frequency? Suppose we make a band very small. Our switching will now become very fast. Is it right? It will reach to upper quickly, goes to the lower also quickly. When the band is less, when the hysteresis band is less, a switching of device will be faster. And when band is more, switching of device will be slower. So we say that the switching frequency of this particular PWM rectifier, is controlled by controlling the hysteresis band. If lower the hysteresis band, higher the switching frequency. So we have to just compromise between the switching frequency and the hysteresis band. Okay, so that we can get our source current will be a sinusoidal, and it will be in phase with voltage, because our current reference we obtain is from in phase with voltage, and that's why our actual current will be also in phase with the voltage. So our sinusoidal current and in phase with the voltage we can obtain. If you want to have a hysteresis control with operational amplifier, then we have to use op-amp as a Smith trigger configuration. Okay, we can use the this is Smith trigger configuration we are having. So we get a reference feedback, both are currents. It is given to a inverting terminal. Okay, and we are having a two resistances with non-inverting and output. And now this particularly, we are getting the hysteresis band value will be a supply voltage of op-amp into the R2 divided by R1 plus R2. We can find out this. Okay, and now here lockout time that is required. So in case of three phase, basically our switches, both switches should not be on simultaneously. Here our switches are okay, switching signal, then also it should not be on. So particularly these two switches, T1 and particularly here it is allowed, but in case of voltage source inverter may not be allowed. So here we require a lockout time. But okay, so that, but here it is allowed, so there is no problem in this case. Now let us go for how to adjust the power factors. So how we adjust the power factor? So power factor will depend upon the VS signal. Is it right? Power factor will depend upon the VS signal. If Vs signal is in phase with supply voltage, power factor is unity. If Vs signal is leading the supply voltage, then our power factor is leading. If the Vs signal lagging the supply voltage, then power factor is lagging. So here it's phase with respect to supply voltage. What is source voltage? Source voltage, this voltage Vs. So it's phase with Vs phase with supply voltage can be adjusted. It can be in phase with supply voltage, unity power factor. If this Vs leads the supply voltage, then our current will be leading. If this Vs is lagging the supply voltage, then lagging. Okay, so this will be our what we are having. We can adjust the power factor. Now next question is, can we use a PI controller for current controller? Can we use a PI controller for current controller? Yes or
Yes.
no?
Yes. Yes, sir.
Yes, but what is the output of PI controller? Here current controller, what we discuss is hysteresis controller that will give direct switching signal. But if you use a PI controller here as a current controller, then output of PI controller, current controller is a DC value. And it will not give the switching signal directly. And for that, from this DC voltage, we have to obtain the switching signal. You just think of that, how we obtain the switching signal for this, we can discuss tomorrow. And now in case of hysteresis control, how we adjust the switching frequency? In hysteresis current control, how we adjust the switching frequency? Anybody? In hysteresis control, how we adjust the switching frequency? Am I audible? Hello?
Yes. Yes, sir.
So how we adjust the switching frequency in case of hysteresis current control? Here we see that, okay, we adjust the what? This band we can call as hysteresis band. If this band is more, our rate of current, increase of current or decrease of current is fixed. A rate of current will determine by the inductor, capacitor voltage and supply voltage. So that is fixed. If our band is more, then time required to reach the will be higher. Also time required to reduce will be also higher. So switching frequency will be lower when hysteresis band is higher. So how we control switching frequency? How we control switching frequency? Anybody?
By changing the voltage.
We control the switching frequency by adjusting the band, hysteresis band. Is it clear now? Here, this band, if you see it here, this is the band we can call it. This is a band, total 2 HB. That is the total band. Is it right? And by if you increase that value, if you make it a band more, if you increase the band here, suppose I'll just show you by increasing the band. If I increase this band, if you made it more, I am showing it here. And if I increase the band like this, let us assume here. So if I increase the band here, then our rate is the same. We require more time to reach, required again this time. So is it clear? So switching frequency will be low when hysteresis band is high. So any questions from your side? Hello? Okay, so we can continue next time tomorrow.